Okay, share slides. I'm actually researching this to answer a student's question. It might be here already or not. Let's see. Anyway, so, all right, let's get started. Okay, sounds good. All right. So this is the last week, and this is sort of like the closing remarks, closing what I have to say about the subject. And so let me say a few words before I dive deep into today's contents. It's been a long semester. If you think back, right? Would you agree? I say that it's a long semester because I feel that I feel the amount of work that you do, even though we're virtual, I don't see you face to face, but uh, for one, I've been through this course for many times, and I know the changes that happens to every student from at the end, at this point, compared to the point that you just started, regardless of your background. Most of you don't have much background in Python. Some of you have some. Some of you have some backgrounds in other, OOP languages such as Java or other web languages, HTML, or not, or maybe C programming in your background, but they are still different from Python programming and much more different from Python for data analytics, right? And by now you would know. So this course is someone would consider a combination of two courses. The first half of the course is to get you as a student from a beginner Python learner to an intermediate, above intermediate level Python for data analytics purposes. We're not here to use Python to develop apps. We're not here to do, testing. We're not here to use Python for scraping or other purposes, but strictly to be familiar with managing, manipulating, and slicing, dicing, doing all kinds of maneuvers, and visualizing data set. And that is exactly what you have focused on. And you have done a great job to this point, but there's still work remaining. As you know, there's a final exam and there's a final group project. I have been getting questions from many of the groups regarding, many of the aspects of the final group project, and just keep it coming, keep it rolling. Don't be shy. If you're shy, start with, "Hey, professor," and then with a little bit, and for me to respond, and then ask a question. Or if you're not shy, just ask a question, or ask a bunch of questions, right? And don't be concerned that you're disturbing me late at night or early in the morning, anytime. It's not like calling me per se. It's different. When I can't see your message, I'll see it later. I'll respond. So with that, we're living in a social media age where these tools, these IT tools, deliver great benefits for our work and life. I think the productivity increased because of these technologies. I appreciate, the functions of these technologies. I hope you also do. So there's work remaining to do, so let's dive into it. That's sort of a quick 3-minute wrap up for the course. Okay, for today, if I'm going to comment a few things about the Jupyter Notebook programming environment. These are not, critical. These may be helpful as you manage your project process. And because of the scale of the project process is supposed to cover the life cycle, right, of the process life cycle of managing a data mining project, the DN process life cycle. So it's a large scale, sort of a full scale project, even it's a reduced full scale project process, if you will. And knowing about these may be helpful. And for some of these, I'm simply emphasizing what you should have known, and to bring these to your attention again, so that you don't, make mistakes or lose time because of making those mistakes in the process of doing the project. And then quickly overview what's going to be expected in the exam, and then Q&A. I expect this to be fairly a long session of Q&A because I'm here to look at the issues that you have. There are going to be some questions that are more general, I know, such as, what's the difference between train test exploit and cross-validation, which I will also comment on here. But if you have additional questions about those, about that aspect, we'll be happy to answer. But I would expect most questions to be more hands-on, or specifically about an error that you have. There's there's an error, we have been trying to debug, can't really get it to work. Can you help me? So I'm here to, I'm expecting to look at your screen, look at your codes and the flow, the process, and then to help you pull out of that trap. If you're in a trap. So that's what I will expect to do. But if you have anything else that need my help, I'll be happy to listen. Also, okay, diving into a few points that I planned to talk. When you make graphs, I'm sure you're going to make some plots. Some of the teams might plot more, some plot fewer. But visualization is something that's very helpful during the EDA process and during the data understanding process. So after you import matplotlib, and this is regardless of whether or not you use matplotlib to make plots per se, or if you use Seaborn. Seaborn is a package that's built on the infrastructure of matplotlib. It just has, I'm getting some echo here. Please mute yourself if you have background that's noisy. Thank you. Again, I was talking about the matplotlib and Seaborn. Even if you use Seaborn to generate fancier, I would say more stylish plots, it uses a foundation of matplotlib. So the magic codes here, the magic commands here, will also affect them. Here, there's a difference between calling matplotlib notebook versus matplotlib inline. This is more of a style difference. The difference is whether or not the plot is interactive. And I have found a post that nicely summarizes some of the points that I'm talking about. And you can see the difference. You may not be able to see the difference because it's not using interactive, but I'll talk about what interactive is. After you have imported matplotlib, you can execute %matplotlib notebook. If you do that, then the plots that are generated, you can interact with it. By interacting, I mean the plots are reactive when you hover your mouse cursor on points on different areas of the plot. It will have floating dialogue or tips on the screen that shows you contextual information about the area that, or about the point that your cursor is at. For instance, if this is interactive, then it will show the coordinates of this point as I move through the area of the plot. You know, it will show 2, 0, because I'm pointing to area where it's 2, 0, close to 2, 0. And then as you move, it will display contextual information about the plot and about the data on the plot interactively. That's what I mean by interactive. But with that benefits, what you my experience, the trouble that you might experience is if you have an issue with the Python session, or whenever you save and close your work in progress, and next time you open a Jupyter notebook, you'll have to rerun the codes that you have developed, and then using the run all menu option is a quick way to run through everything. But with the interactive plots, you might experience issue where the running process may stop at, or the running process may run the codes of the plot, but the plot doesn't render appropriately. So that is the issue I have experienced. I'm not sure if that is universally happening, but just to be reminded that this might happen. On the other hand, if you use inline, then the plot is not interactive, and then the run all menu option will work very well. The plot will render every time. But here there's something to keep in mind. You want to put everything about this graph in one cell, because the fact that it's not interactive, it also loses the capability to be cumulatively built. The graph is not cumulatively buildable, meaning if you have one cell that generates the frame of the plot, and then second cell adds a line, third cell adds some legends, such as such, that capability would not work with inline, may work with the notebook, interactive, or several other styles of the matplotlib. So be informed about these differences. Regardless of which one you use, I caution against using multiple different styles. For instance, you use interactive in the beginning, and then later you switch to inline. Don't do that. Stick to one style from the beginning to the end in the same Jupyter notebook. So that is one thing about the magic commands. There are many other useful magic commands. Not going to, probably not worth going through one by one, because you probably never use some of them. But one thing is that the display, I use display quite a lot. The benefit of display is when you is that when I want to see a snippet of a data frame, I would like to see it as formatted as a, shaded table format. So that doesn't happen when I use print data frame. It's printing plain format. You know what I mean, the shades between lines, the shaded line, the shaded columns, that's a nice feature to look at when I want to review the data set, the values of the data set closely when I print a few rows. You can do that by simply calling the data frame, say df1, execute the cell, then you get a snippet of the data frame. But what if you want to display several data frames in one cell? You don't want to, because all of those are, already, you want to just look at them all at once. Then the only other way to use is print, but again, print doesn't have that shaded format. So display is good in the sense that you can put the 3 or several data frames as a tuple, use comma to separate them, and then put them all within the display. Then it nicely shows each one in a sequence. I'm sure you've seen those codes and examples in modules. But here's the point. You can use the display without any issues in Jupyter Notebook, but if you leave the Jupyter Notebook environment and try to program Python such as in native shell, native Python shell, or other like Eclipse, other IDE, then display is not by default imported. Display is a utility of IPython. IPython is basically the backbone of Jupyter Notebook. So by using Jupyter Notebook, which is IPython based, you get the benefit of having display without having to import it. But if you want to use display in other IDEs environment, then you need to import display by importing from the IPython package. So here is one example. This is by using a Windows command. I can show you quickly about that. So I'm going to bring up the Windows command the same way that you bring up Windows command every time you open the Jupyter Notebook. I have just opened the commands. Here it is. Hopefully you can see it clearly. It's kind of small, but maybe I can make it bigger. Okay, sounds good. Now, so you use this to, to open a Jupyter Notebook. But here I'm going to open Python, right? And you did this the first time that you opened, the first time you installed Python. You did several of these testing just to make sure that the Python is the right version of Python is installed. Most of you have 3.6.4. Some of you have more latest versions just because you use Mac or you use Conda, other virtual environments. Anyway, so I'm in Python here through the Windows command. And we can do a few things just as we do in the Jupyter Notebook. So I can import. Of course, here you lose the contextual functions like colored, color coding features and other things like tab completion. You don't have those, and auto indentation. You probably don't have it either. So it's a very plain programming environment. Anyway, import numpy and b import pandas as PD. So this feels more like in the old times, you know, the DOS system. Anyway, okay, quickly generate a numpy.a range. Quickly generate a sequence from 0 to 20 with capital 3. How many do I get? 6 numbers. Oh, yeah, this is what happens. If I need to specify a gap, I need to specify a start. Okay, 7 numbers. Things like that. So, if I want to maybe make a quick array, then is exactly what I did. So array 1, and then if I want to display array 1, it didn't work because display is not defined. It doesn't recognize display function, okay, the command. So here I can do from IPython, take a peek, and I do it from IPython display, import display. Now I have display and hit up, recycle one of the commands. It does display. Great, it displayed the content. It's very similar to print, or exactly like print here, because in the command environment, you don't have those visual, all those visuals are gone. So display doesn't make a difference, but sometimes you just want to be able to execute that without having to change your codes. The extra step you need to do is to import the package and the command. All right, that's it. Exit Python, close, and then come back to slides again. All right, here's a link. I believe you have the slides, right? On Blackboard, it's the last slide. So you can access the, let's see, the links to full list of commands, magic commands here. Anyway, all right, pipelines and column transformer. I'd like to say a few things here. For data pre-processing, for students in this course, because you are at a more advanced level of data analytics using Python programming, so you are at a higher platform to kind of, more easily, hopefully more easily, and more effectively understand how pipelines work and how to use them effectively. Okay, so here the both the examples demonstrated in the module as well as your project, the data set, in both cases, the data set is sophisticated enough that your data pre-processing process kind of can leverage. It has room to leverage pipelines and transformer in a way that allows you to understand the full scenario. So for example, what I'm talking about is that you have nominal variables that are that requires creating flag variables to model the different levels. Otherwise, with the different levels, with the distinct levels of the nominal variables, it is not easy to numerically represent the variations of the different levels. A common mistake would be a amateur analyst would be a common mistake would be to number code, numerically code with different levels and simply treat it as numerical variable. It is just a no-no. you'll laugh at it, given that you have gone through this course. But it is a common mistake because Python will not report errors. You know, if you assign arbitrary numbers to it and scale it by using standard scaler, Python is not going to report errors. So it looks like it's fine, but it's not fine, really, by the way of data science. So you have nominal variables, and those variables might have missing values. So you need to impute the missing values, and then afterwards you need to do dummy coding. Another scenario would be that you have an interval variable that has missing values, and then after imputing, you need to apply one way of standardizing or normalizing the column. It can be min max, or it can be z standardization. And here in the module, I also talked about the logarithm transformation, which is not always necessary and may not always sort of help with modeling, because I guess the effect of logarithm transformation is more theoretical than hands-on. I'm not saying it doesn't help, and I'm not saying it always make things worse. That is not what I'm trying to say. What I'm trying to say is to really understand the effect of logarithm transformation. It has more theoretical flavor than empirical flavor. But regardless of what kind of impact, the impact might be really small on your model. So maybe it's not something you need to really worry about. Does it really make an effect? But you make your judgments on another criteria, which is there severe skewing in your input variable? If your interval input variable is severely skewed to the point that you have such large values, extreme values that are certainly outliers, but this is the outliers of the outliers, if you will. It is 200 times more than the mean, things like that. What do you do, right? Do you throw that data point? That's not something we really advocate, and there are good alternatives to do other than simply dropping the data point. Just because of this variable, you drop the data point. The better alternatives would be to use logarithm transformation to, dramatically reduce the amount of outlier in that data point. The nice thing about logarithm is that it's exponentially reducing the scale. So any extreme value would look like a joke for logarithm functions, because it really does a job, and in bringing outliers closer to the mean. So that would be the criteria I suggest that you stick to when you decide whether or not you apply the logarithm transformation here. So both in the I would say more in the class project than the demo project, you have reasons to use logarithm transformation for some of the interval variables, such as square roots. Some of them are really big. Okay, so now you have at least 3 groups of variables that you need to apply different pipelines. A pipeline is a set of transformations. All the things that I talked about in the need for doing something to pre-process the data, most of them are transformations. And we use transformers as a category of tools to pre-process the data. So a pipeline is a set of pen here is a set of maneuvers connected together one by one in a sequence. So this pipeline has simple imputer as the first maneuver, simple imputer. And after that, it will return the a NumPy array with the missing values imputed according to the rule that is set by the simple imputer. Strategy that here it's using median because this is for interval variables. Median is better than mode or mean. So the intermediate result will be the imputed data set, and then the pipeline will then import this intermediate data set into the second step, perform this custom function transformer, and you define the function here. So here, this is more like a custom function, and the custom function is logarithm transformation. And then, outputs not output, but processes the intermediate result and then input to the third standard scalar. And then in the end, through this pipeline, input in, output out, with the columns that are named for, that are named for this pipeline object to process. Everything else, appropriate things will be done. So that's pipeline. This pipeline is specifically suitable for those interval variables that needs logarithm transformation and potentially has missing values and must go through de-standardization. Here, a critical point I just remember is that even if your training set doesn't have missing values, it doesn't mean it's safe to drop it, because you might have missing values in your test set, and you might have missing values in your score set or unseen or holdout sample. What are you going to do with that? You can't guess the what kind of values to impute, right? This simple imputer is here to accommodate to those situations where you might need to impute. So this is a sort of an insurance step that that I would strongly advise you to keep in every pipeline when you use transformers to pre-process your data for your data mining projects. Right? Think about the unexpected situations. And here, that is exactly the situation, because you have missing values in your score data set. So by having imputer in your pipelines, if you use transformers, by having simple imputer as part of the pipeline for interval variables, as well as nominal variables, another pipeline for nominal variables, you take care of those problems, right? So this is one of the nicest things about data preprocessing, which is it makes it very easy. It makes it very easy. So that's the point. One last point is that remember to use fit transform on training data, provided training data here, replace everything, including the less than and greater than symbol with the training set. And then after it is trained, pipe, after pipe is fitted to the training set, then use it to only transform the score set, as well as if you have a test set, if you have a validation set, if you have, let's say, sets, if you have holdout set, you know. So fit transform is only supposed to fit to the training set, and everything else you should use the train transformer or pipeline. Use transform. All right. Any questions? This point is both important and big, and may be confusing. So I want to make sure cover any questions that you might have. All right, probably no questions, but good thing you can review when you need. All right, so why do you need pipelines? Why do you need, sorry, you have pipelines, why do you need column transformers? Because a pipeline only takes care of one scenario. You might have several scenarios, then you can build different pipelines that might share the same thing in the middle, but altogether the pipeline is different. It has unique combinations as well as sequence of different transformers in there. So take this example. For the 3 scenarios demonstrated in the module, you have 2 pipelines for interval variables. The difference is that one of the pipeline has the custom function, which is the logarithm transformation, the other doesn't. So any variables that has severe skewing, you're advised to include those in pipeline 1. Whereas all the other interval variables that does not have severe skewing, I suggest you to put them in to use type 2. You know, how do you specify which one to use? You put them in the column label list that you call when you call the pipeline. So every pipeline should have a corresponding label list to indicate which input variable column to apply which pipeline. The third pipeline is for nominal variables. All of these has imputer, as this should have imputer, right? Be mindful about that. And the imputation for nominal variables, it's best to use the most frequent label to do imputations. All right. After you define the 3 pipelines, you provide the column lists to invoke the pipeline as, you know, part of the tuple for the transformer definition. You use make column transformer and then put them in tuples in parallel, right? And make sure you cover all of them. If you have some of the columns that do not require, or it's best not to, or shouldn't be transformed, such as an ID column. Let's say you have an ID column. It's in the data set, it's in the data frame. It shouldn't go through any of the pipeline. That's true. So in that case, you would include, we would have a 4th column list, which includes those column names, and you specify here after the last comma, you specify remainder is passed through. Oh, you probably don't need a 4th label list because everything else will be passed through. All right, so revise one extent, you only need 3 column label lists. Okay, and also remember that you should only fit your transformer or pipeline to the training sets, and everything else should use transform, right? So in wrap up, here is what a column transformer is. A column transformer may have several pipelines, or pipeline may be transformers. So column transformer can have can be consisted of several transformers as well. It doesn't have to be pipeline, but most likely you will need pipeline, right? And pipeline, each of which consisted of several basic transformers. So transformer is a bunch of transformers. Like, it's a little bit convoluting, but anyway, you get the point. This is fairly complex concepts and quite extensive coding, as you have seen in the module. If you spend the time to try to understand the process and work it through by using the different the different materials and the data sets, then you become more familiar with the process. So this is a very worthy learning process to go through. Right? So the pipeline plus column transformer process versus manual processing, they have pros and cons, of course. Pipeline is good, column transformer is, it's powerful, but for very small projects and very small data sets, it probably isn't worthy to bring the elephant, so you use manual processing for smaller data sets, but for a large scale data set and for projects, for models that you expect to reuse the model after you fit it to make predictions over and over and over on new, continuously flow in unseen holdout data set, then on every piece of or every data set of the holdout data set, you're supposed to pre-process them. You can't simply make predictions, after you get a new data set, even if your model is ready. Your model is ready because it's accustomed to the data set that has been pre-processed in a certain way. You have to prepare your new data set before it's ready to be predicted. Otherwise, you can predict, but the numbers would not be consistent with what the model expects, right? And that's it. If you're only going through a small-scale experimentation process, then manual processing should also work. One last comment here: if you use manual processing, then all the imputer scalar, 1-hot, 1H, 1-hot, encoder, all of these, you fit transform on training set, but then only transform the score sets or test sets. You get the point, same point repeated. All right, so enough about that. Well, one of the last points here is the difference between train test split and cross-validation. These are actually from a complete supervised learning data mining project process. They are referring to actually two different stages. Even though you can repurpose train test split to do the same job as the cross-validation, but after going through this class, this class is sort of an advanced version of data mining than the framework class. So that's why I talk about cross-validation. Cross-validation is more powerful in terms of dealing with overfitting, which still possesses the fitting curve characteristic. So you have two things in one. It's like a bundle. But then train test split happens very early in the data understanding stage. You get the data set, you do some surface level understanding and cleaning, and then right away you do train test split to preserve your test sets and never touch it again until you have your model ready. You almost are going to go with it. As the last final check, you use the test set to verify your model is relevant. That's the sole purpose of the test set. It's not supposed to be retested over and over and over. So that's why you do train test split very early on so that you don't do too much exploration on the test set. If you do too many explorations on the entire set, then you kind of have too much knowledge about any subset of the entire set. And then if you do train test split by then you have much knowledge about the potential test set, right? So before you do any deep level understanding or cleaning, you do the train test split. You know, and later on you use cross-validation to test different models, to evaluate different models, compare them, choose the best one, and maybe further revise and retraining, refitting, and then update your model selection. That's the purpose of cross-validation. It's supposed to be used and tested over and over and over. That said, the train test fitting curve is different from the cross-validation curve. The train test curve is like this. When you have a training set and a test set, and let's say this y-axis refers to model performance. As I emphasized, there are two ways to make a fitting graph. One way is to plot the errors on the y-axis. The other way is to plot the model performance or accuracy. Accuracy as an example, which is the model performance. So depending on what the y-axis is, x-axis almost always denote the model complexity. So if it's model performance, then one line continuously go up and maybe plateau at some point. The other line go up first and then reverse and come back. The line that continuously go in one direction is going to be the train set because it has opportunities to be overfitted. The other line is what we call validation. So notice that I'm not calling this testing set because I'm trying to be consistent with the notion that testing set is only supposed to be used only once, maximum twice. Because you use a test set only if you have a model that you almost would go with after trying many different things. So if that's if that's the sole purpose of testing set, then you wouldn't be able to see a line of testing set being tested over many generations of the model with different complexities to get a curve. So you wouldn't get a curve, you will get a dot for test sets. The dot potentially may be at here, you know. It is a similar complexity model and similar let's say it's here. The dot will be close to here. It's a final testing of the model reliability. But if this is a validation set, then this validation as well as training sets would all be coming from the train section, the train set, the grant train set after split set has already been preserved, right? After train test split, you flip train again to get train validation. Then you are able to plot something like this and to look at the overfitting happening. All right, so this is the train test split fitting curve. In comparison, the tenfold cross validation curve looks like something like that. This is a screenshot from the module, as you would probably notice by this sharp dip. A few things to clarify here. On this graph, it compares two models. And this is the point in the module was to kind of test whether or not having one more meaningless input column would actually hurt the model of prediction performance. And it kind of did, because it lowered a few of the folds performance. This is the performance measure. But here you don't see that true diverging curve clearly. And why? Because this is one model, as versus in the fitting curve of the train test split, you have many models. This is complexity of the models. Every dot that is used to make the plot represents one different version of a model. You are increasing the complexity of the model. That's why you have different results that you can use to make. You can plot the performance, and then you can connect them to make two curves. Here, the curves are performance of two models on different folds. This is sort of like going and zooming into the results because you have multiple folds. If you average them, the two model will be virtually inseparable, and it's just one dot. Actually, it's not two lines. But if you aggregate them, it's going to be something like here. The two models have performance, and these two dots would be similar to two dots that can, form a curve, because these two models are different versions and they are using the same set. So this curve is quite different from this curve, quite different. This curve goes into the details, it goes into the folds, rather than showing the aggregate results. And then this is not two lines, this represents actually two different versions of the model on the same data set. So you would actually connect those two dots. In this context, they will form one curve. Hopefully that clarifies the confusion. And one last point. You are, and maybe because of the confusion that some are having, that some may think that this is the curve, then you are supposed to pick one of these models, but not really. This is just one model, two models here. You are not going to pick the fold. You are not picking the fold. The 10 folds are holistic. The 10 folds, the purpose of 10 folds is to sample differently, to allow variations to potentially test your model. But then you're always supposed to aggregate the results of the 10 folds. If you have 10-fold cross-validation, you're supposed to aggregate the result of the 10-fold and take that aggregate evaluation metric to evaluate your model. You're not supposed to pick folds. So don't be confused in that respect. All right, so lastly, if you have, therefore, cross-validation, and if you train multiple versions of the model, here it's a k-nearest neighbor, as you would recognize, you probably get one of these curves. At some point of the k, given the same set of input variable columns, then your model achieved the highest performance measure. Here, the performance measure is the negative mean squared error. And when you increase the k, the model becomes when you increase the k, you include more neighbors, and then the aggregate is more representative of the entire data set. The model becomes more generalizable, but the model is not more generalizable. The model becomes simpler, sort of converges to the average, and then performance goes down. If you decrease the k, the model becomes more unique, caters to specific points, and maybe overfitting. So, go in both directions, the model performance goes forward. Here, how are we able to choose the best model simply based on one line? This is because cross-validation is like the validation curve. Cross-validation has built in the split by itself, right? Cross-validation is taking folds and training on nine folds and test and validating on one fold, and then do the rotations. So the mechanism already embeds the sort of like the train test split mechanism. So in the end, when you look at the aggregate results over different versions of the model, you have one line that's sort of like the validation line curve, validation curve. And you don't have the training set curve because the training set performance is not being generated. If you were to generate that, then this is underperforming. This is underfitting. It's supposed to, let me change the color. No, sorry. I'm not paying, so I don't get to use the fancy versions. Sorry, I only have black. When the model is underfitting, you have this line, it increases, and it may be crossing, that's fine, as long as it goes up. But then the model approaches the peak as the model actually has the highest generalizability. But if you keep catering to unique points, your line may still keep up because that's the training set. Okay, so if you have the training set curve here, it may look like that. Therefore, there will be a divergence, right? But in the context of the cross-validation, you don't need two lines. You only need the validation. Okay, hopefully. And if you have cross-validation and then you still want to include the training test split, then, as I said, I suggest you to do training test split very early on before you do the heavy EDAs, and then preserve the test sets, and then do the pre-processing using the transformers, and then use the fitted transformers to process the testing set, to do transformation, right? To transform the test set and then leave it there, and then do the training, evaluation, and selection using cross-validation. And then once you have your final model, then test it on the test set, and then simply, compare the the model evaluation metric quickly from the test set with this, the peak point of your selected model, and to see whether or not they are close. They don't have to be, they cannot be exactly the same because that's two different sets. But they should be close. If they're not close, then something is wrong with here, and you want to reconsider the process, and then maybe debug, maybe try to find hidden issues. So happy to talk more about this process, but not every team is going to use train test plate, because I do consider that's a challenge. That's also a deviation from the process that's outlined in the modules. So not every team is best positioned to do this, I would say. So if you're not ready, I discourage you to do that. Only the teams that are well versed can try this, but try this at your own discretion, at your own risk. I'm here to help for sure. But that's that. Okay, for the final project, or the several topics that I highlighted for the final project. Any questions? If you have coding error debug related questions, let's talk wait after I have talked about the exam, the final exam. But if you have general questions about the project, let me know. Any questions about projects? Messages. Great. All right, no questions at this point. So let me keep going about the exam. So I'm showing the prep guide for the second exam. You probably have already seen this and downloaded this. Review this, but I don't suspect any surprises to you. I want to say that something that's not specifically mentioned here is that if you look at the guides here, you have conceptual topics and hands-on topics almost evenly split, and the exam will reflect that. So do expect a good portion of the final exam to be conceptual questions, meaning multiple choices, short answers, and true or false statements. All right, so conceptual questions are important, especially for the second portion of the course. But it's not saying hands-on are not important, and that's why the rest of the exam is devoted to the hands-on. And for hands-on questions, these questions will be more comprehensive, more holistic than the hands-on questions in the first half, which are more spontaneous or different scenarios, because that is when you were a beginner and now you are more advanced or intermediate level data analyst. So these hands-on questions will reflect the kind of questions that you have in the homeworks and the hack shots problems, which are typically based on a data set, and then you analyze the model, you you analyze the model, you maybe dig deep into the data set, you interpret the results, make recommendations. So these are going to be that kind of problem. And in those questions of hands-on problems, you might also expect some conceptual questions that ties to the data and reports. Ties to the data and the model outputs and model results, interpretations. So that's basically what to expect for the last exam. The last exam will run for 2 hours. I think the first exam ran for 2.5 hours, slightly longer. When you're more beginner, and now you're more advanced. And the second exam is less about intensive coding, so it's shorter. It's more has a lot of conceptual questions. All right. Any questions at this point? I'm going to stop sharing the document. You can download it from Blackboard, or in the future, it will be on Canvas because it's recording. Any questions about the exam? No question at this point. Then let me take a look at my slides. The project is due this Saturday night. So mark your calendar on that. I think you're very accustomed to the few weeks during the final stage where you have projects due, presentations, and then finals. But since you have a lot to manage, mark your calendar about Saturday night for the project for this course. And that would be all that I have prepared to present. And for the rest of the session, I'm here to help you on any challenges and specific questions on your project. All right, I will open this up to questions. If you need help to solve a specific errors or coding questions, and then be prepared to share your screen. And we may use some of the remote control functions here. So just be prepared to share your Jupyter notebook. All right, any questions? If you don't have questions, then you can use the time to work with your partner teammates to make progress on your project. All right, I'm all ears. Anybody? Anybody has any questions?
A question, Professor.
Who's speaking?
Hani.
Hey, honey.
Yeah.
What's your question?
So I did 2 pipelines for processing the training data set. And I want to ask about applying the transform function on the scoring data set. So I need to do the two separate columns again, and apply 2 pipelines with not with fit transform, but with transform only, right?
You mentioned that you have 2 columns. What do you mean?
I mean two data sets, one for log transform and one for numerical variables or nominal variable. So I did 2 pipelines. What I mean the column labels. So I did 2 variables with two different columns.
That sounds right. Yeah.
Yeah, and for the scoring data, I need to do the same, right? And do a transform on both the pipelines.
Right, just right. All the transformers, you only need to define once.
Yeah.
Once, right? And then when you transform, depending on what other data sets that you have, most teams typically will have only a score set. So you only use transform, dot transform only once. And that's because it's on the score sets, the input variables. Sounds right?
But if you use two pipelines, do you define two different pipelines?
When you have two pipelines, then you will use a column transformer to put them side by side, right?
Yeah.
Because the
Yeah.
pipelines are parallel to each other, applying to different sets of variables. Then once you have the column transformer, then you don't directly deal with pipeline anymore because the pipelines are parts of the column transformer. The column transformer becomes the handle that you deal with. Then you fit your column transformer, which has a pipeline. You fit your column transformer to your training set, and then you only transform. You use that fitted column transformer to transform your score sets. Done.
All right, thank you, sir.
Sure. All right, nice. Okay, so let's adjust the plan. So it looks like there is no specific coding questions or challenges or errors that need debugging at this point. What we're going to do is we'll release the time for you to work on anything that you want. By using the time, you can work on a project. It's a nice time to do because the time is set aside. Or you can do your own study or use time elsewhere. When you have questions, when your team have questions, we mostly use team because you can post screenshots. And in fact, whenever you ask a coding related question, whenever it involves a debug or if it's a difficulty writing the code, always provide screenshots with details, with contexts. If there's an error, don't just, not always, sometimes only post the cell that generates the error. But sometimes you might be prepared, you need to be prepared to provide more screenshots of the cells preceding it because sometimes the problem is deeper in the process, not immediately caused by the cell that generates the error. You know what I mean? Because we're dealing with data objects, we're not dealing with simple commands. So, leave messages in Teams, include your TA EVA as much as possible, almost always, unless it's a personal question. And then if needed, we can schedule live meetings to discuss about challenging problem. All right, sounds good. Any other opinions or suggestions? Sounds good. Okay, so we'll call it a night for now. We'll adjourn the class. Teams, make use of the time or make your own planning. Let me know, let TA know when your team has a question or when you have a question about the final. And then I'll be looking forward to see you sooner, hopefully sooner than the final exam next week. I'll be sending out a meeting invite for everybody to join for the final exam. Sounds good. Okay. All right, meeting adjourned. Enjoy the rest of the night. Enjoy your hard working. I'll be here to help. Great. Now, we'll stop recording.